Okay, welcome everyone to today's AI4OPT seminar. It's a pleasure to have Professor Lei Ying. Lei is a professor at the ECS department of the University of Michigan, Ann Arbor. He's an IEEE Fellow and an editor at large for IEEE ACM Transactions on networking. His research is broadly in the area of stochastic systems, reinforcement learning, graph mining, and communication networks. His work has received several awards, including Best Paper Awards in IEEE INFOCOM and ACM SIGMETRICS. So without further ado, Lei, the floor is yours.
Okay, thanks. Thanks, Dabanku, for the nice introduction, and thanks, Sevcik at Dabanku and Sushil for inviting me and organizing this visit. And I really enjoy the weather and the campus. I have to say I was expecting warmer weather, but still it's warmer than Michigan. Okay, so today I'm going to talk about safe online learning and decision making. Yeah, so my talk will be organized around 4 questions. Okay. The first question is, why is this problem worth studying? Basically, I would like to give you motivation for looking into this problem. And the second is, what are the fundamental differences between constrained and unconstrained problems? Then I would like to tell you how to achieve sublinear regret and zero violation with a model-free approach. Then at the end, I would like to also present a result which can even do better than the first one. Okay, so let's get into the first question. Why is this problem worth studying? Okay, so we know like reward or cost-driven learning and decision making have a lot of applications in AI, in big data analytics, and so on, right? So here are a few examples, like Bandit has application in recommendation systems, and has application in clinical trials where we try different drugs to see which one is more effective, right? Then online convex optimization can be used as a theoretical tool to understand the training of large-scale machine learning models, and can be used to design an algorithm for federated learning and so on. And reinforcement learning, and we probably see lots of news around reinforcement learning, let's say AlphaGo, and also use reinforcement learning for fine-tuned language models and so on. Okay, so we can see it's a very practically important area doing this learning and decision making together for improve the performance of real systems. Okay, but when we see more and more applications of these theories, this algorithm, we also realize when we use this algorithm, all right, in real systems, then it's not only we want to maximize the reward or we minimize the cost. There are other things we have to consider. Actually, the system had to be operated a range of operational constraints. For example, if you look at the Bandit setting, and if you look at the ad placement, then there's a budget constraints come from a customer, or they have a fixed amount of money to spend for buying those ads. Then we need to optimize our decision based on the budget constraint, right? And if we look at using machine learning model for risk assessment, for example, for assess the risk of mortgage loans, then we need to realize our data may have different distribution over different populations. So we may have like a minority population and minority population. So the decision will have actually a consequence of how these populations will do after they get this mortgage or be declined by this mortgage, right? So there's a feedback loop. Therefore, we need to be mindful and design algorithm, which is not only just maximize the accuracy, also be fair to different populations, right? Then if you look at these AI-powered drones, autonomous driving, then we also realize sometimes even reward is not even the first order consideration. We need to look at other constraints, for example, safety. We need to first make sure safety, then talk about maximizing the reward. And also, given we're using AI like a black box AI foundational model to make a decision for us, we also need to be careful about to align the AI decisions with the human decisions, right? This becomes another constraint to consider. Okay, so therefore, that's motivated us to consider the safe online learning and decision making. So safe here basically stands for constraints, right? So you need to design the algorithm with different type of constraints in the mind. And online means the algorithm have to be adaptive because this application will be deployed in a dynamic and uncertain environment. Things will change. So we need to have the algorithm which can react to these changes and adapt its decisions to optimize the performance. So that's why we want to consider both safe and online learning and decision making. Okay. So now what's the goal here? Okay. So the overall goal here is to design algorithm which can safely learn a safe policy. So there are two safety notions here. So the first one is a pretty common one. It's a conventional one. It's called safe policy. So the policy safety. So which means the learned policy need to be safe, or learned policy has to satisfy the variety of constraints we have in the problem formulation, right? So if we look at this cartoon picture, right, we have this policy space. This green subspace is space for safe policies, and this red dot is optimal safe policy. Then the first goal here is to find agents that learn a sequence of policies eventually reach this optimal safe policy, right? So that's the first safety notion. Then the second safety notion is also we want to safely learn that, which means we also need to consider this exploration safety. For example, here we have two learning trajectories. The first learning trajectory goes to some unsafe policies, but very quickly go into this set of safe policies and converge to the optimal safe policy. And the second one goes all the way outside of the safe policy regime and at the end converge to this optimal safe policy, right? So clearly the first trajectory is more preferable than the second. Okay, so we also need to consider the safety during the learning and consider how much risk the agent has to tolerate during the learning process. For that, we are looking at the regret and the validation. Okay. So hopefully by now, I reasonably motivate you why this problem is an interesting problem and why we should look at it, right? So also not only from application perspective, if you look at the problem itself from a theoretical perspective, the problem is also very interesting because it has multiple dimensions, right? For example, from the complexity of the problem itself, we can look at from the banded setting, then make it more complicated, look at online convex organization, then look at online control setting, then you have the full complexity in the reinforcement learning, right? Then also from constraint perspective, that is another dimension, we can consider a variety of constraints, right? Some constraints are hard constraints, some constraints are soft constraints. So for example, what are hard and what are soft constraints? For example, if we look at a violation, we could consider those violations which can cancel from one episode to another episode. For example, budget. So if you use some of the more money in this round, but you save in the next round, then overall the budget constraint may be fine. So they can cancel each other. Then this will be the constraint violation, right? And you can also consider hard constraint, which means, for example, look at the side effect of particular drug. So then you look at the patients. Those patients have severe react to this drug. We're gonna look at the violation, right? And if there's no reaction, I mean, no side effect on certain patient, you don't want to cancel them with those patients has a significant side effect. Then in that case, you evaluate this constraint in this hard sense, which means you only add up those violations without offset with these negative violations, right? So then in those cases, soft and hard, you have different algorithms and you have different fundamental bounds. So each of these combinations, right, complexity of the problem and the type of constraint will give you a unique problem, and you can get like multiple papers for each of these settings, okay, for sure. So that's why also theoretically, it's a very interesting problem, okay? So in today's talk, I'm gonna focus on one specific combination, okay? So I'm gonna look at this reinforcement learning problem under stochastic and soft constraint, okay? So let me tell you now what are the fundamental differences between constrained and unconstrained problem for CMDPs, okay, for constrained Markov decision. Okay. Any questions? Okay. So let me first tell you the setting. Okay, we look at a setting which is episodic MDP, and at each time the agent start from step 1. Okay, then at each step the agent takes an action, then the agent receives a reward and also receives a utility. Okay, then based on the state action, the agent moves to the next step and goes into a different state. Then the agent takes another action, receive a reward and receive a utility. Then agent goes to the next step and so on. Until at the end of the episode, which is step H, then the episode ends and we restart the episode. Okay, so that's the setting. Yeah.
What's the difference between reward and utility?
Yeah, so you will see that. Okay. So that's a good question. What's the difference between reward and utility? They both are real numbers. Okay. And the formulation is we want to maximize the reward, but with the constraint that the utility has to exceed certain threshold. Okay, so utility basically are the ones which give us the constraint. Okay, so we can have multiple utility signals. Each of that we can have separate. Okay, and here I pose the constraint in a form like the utility needs to be greater or equal to certain threshold. Because that's the convention in CMDP, we look at this type of constraints. But you can very easily translate that to be the cost less than equal to certain threshold. They're almost equal. Okay? But by following convention, we are considering the utility greater or equal to certain threshold. Okay. So this is our CMDP setting. So we want to maximize the reward and subject to this utility constraint, we are looking for an optimal policy. Okay. So if we remove the constraint, that's just the traditional MDP problem. So now let me tell you what are the fundamental differences between MDP and CMDP. There are actually a few of them are quite interesting. Okay, that also motivated myself to get into this area. Okay, so the first one I want to mention is I think most of you who work on MDP or bandit type problem, or even have taken the class in dynamical programming would know that, right? So one foundation or the most important foundation behind reinforcement learning is called the Bellman equation. So where the Bellman equation come from is this principle of optimality. Okay. So what is principle of optimality? It says if I have an optimal solution for my unconstrained problem. Okay. If I look at a sub-solution from my optimal solution, that sub-solution has to be the optimal solution for the corresponding suboptimal subproblem, right? So let's say I'm looking at the shortest path problem from step 0 to step H. Then if I have the shortest path, then if I look at a subpath from the current step to a destination, that subpath has to be optimal as well. Okay. So what I mean, that means if I look at what the decision I need to make in my optimal decision, I don't need to actually worry about the past. I don't need to worry about how do I get there. I only need to worry about what I need to do in the future, right? How do I get from current state to the destination, right? So why is this important? Because that basically gives us the Bellman equation, or this, for example, this Bellman equation for this Q function, right? So Q function in state I, by taking action U, is the reward I will get plus what's the optimal value I get by following the optimal path from the current state to the end of the episode. Okay. So again, I want to emphasize how do I get here? That's not important for solving the sub-problem. Only the future is important, right? And why this Bellman equation is important? Because that is the equation we try to solve in the reinforcement learning algorithm, right? So for example, our Q-learning algorithm, SASA algorithm, the deep Q-learning algorithm, DDQN, and you can list all these kind of algorithms. The focus of all these algorithms is solving this Bellman equation and find a policy which can satisfy this Bellman equation, right? So therefore, it's not an exaggeration to say this is basically the fundamental mathematical foundation of reinforcement learning, together with many others, right? So now let's look at the constraint problem. Look at why things is different. So unfortunately, in constraint problem, we don't have this principle of optimality. Why? Because we have budget, let's say. So therefore, how do we get here become important? So for example, if I already spend $1, I have $10 to spend. I spend only $1 to get to the current step. Then I have many choices to get to the destination. So I can choose some expensive route. I can choose some cheap route. Then I have more choice, right? Compare the case if I already spend $9, I only have $1 to spend. Then I only have limited choices for the future. Okay. So therefore, in constraint problem, unfortunately, we not only need to look at the future, we also need to worry about the past. So the past and the future actually are coupled in the constraint problem. So we don't actually have these nice Bellman equations. So that raises the question then, what is the objective or what is the guide principle we can use to solve our problem? Okay, yeah.
Can you just add the remaining budget to your state?
Good question. Exactly, I know the question will come up. Yeah, you can. Of course, if you add the budget into the constraint, then it becomes the MDP problem, right? That's brilliant. But what's the consequence of that? So let's say if you have a finite state, finite action problem, if you add a budget, which is a real number, you immediately go from finite action state space to uncountable action state. So in general, it's not algorithmically a good idea to model that as a state. Okay. Any other question? Good. Yeah. So that's one fundamental difference. And the second fundamental difference is from solution perspective. So in general, we know like at least for tabular case for MDP, one of the optimal solution is greedy. So that's why we can use like a value-based algorithm. We learn the value, we take greedy decision based on value, then we recover one of the optimal solution. Unfortunately, in the constraint case, in most of the cases, greedy decision is not optimal. You have to randomize, okay? So here is an extremely simple example. Let's look at the bandit case, where you have one worker, she has average reward 1, another worker has average reward 0.5. So now let's say it's unconstrained. I want to find the best worker. Then I go to worker 1, right? So it's a greedy decision. The policy is 1. Okay. So now if we have cost, let's say the salary I have to pay to the worker. The first worker has a salary of 0.8. The second worker has salary of 0.3. Okay. So now I want to maximize my total reward with a constraint that the average I want to pay is no more than 0.5. Then you can verify none of the greedy decision will be optimal. The optimal decision will be use worker 1 for 40% time, worker 2 for 60%. Okay, so you have to randomize in CMDPs, unfortunately. So you cannot get greedy decision. Okay? So these are the second fundamental difference. Okay. Then because of these fundamental difference, you can imagine if I now use value-based solution, let's say use Q-learning, they will not work because Q-learning tell you the value, but the value will not uniquely map to the policy, right? Because greedy decision based on value will not give you the optimal policy, and only knowing the value, you don't know how to randomize that. Okay. And because this second difference, there's also a fundamental difference from learning perspective. So we know, for example, in a bandit case, if the bandit is a well-separated bandit, which means the gap between the best arm and the second best arm is a constant gap, right? Then we can usually get a log regret. Okay, so even in MDPs, tabular case, you get log regret. But even for well-separated CMDPs, which means well-separated means the actions, different actions will have different reward and different cost. Okay, so they are not like very close. So even for well-separated CMDPs, you cannot get a log regret. Okay, so the regret has to be much larger, even for well-separated CMDPs. So here is a very simple example. Okay, so example 1, the example includes 2 instances. The first instance is basically the one I talk about. The worker 1 has reward 1 cost 0.8. Worker 2 has reward 0.5 and cost 0.3. Then I have a second instance, which is very similar to the first one, except the cost for the first arm is slightly larger by amount of 1 over square root k. Okay, so what happens in that case? So now let's say if I only have k over log k samples, because we know the difference between, sorry, you get used to this pointer. So let's assume the distribution of Bernoulli, and these are the mean of the Bernoulli distributions. Okay. So now let's say if you have k to the over log k samples, because the mean difference is 1 over square root of k, so you know with this amount of samples, it's very hard to differentiate whether it's instance 1 or instance 2. Okay, so these two are almost indistinguishable with the amount of samples we have with high probability. Okay, so let's assume this is the learning horizon. We look at k over log k pools here. Okay. So now you can define this C to be the expected number of expected frequency of pooling arm 1. Now you can plot this very simple picture about how the regret and the violation changes as you change this value C. Okay, how if you spend more resource in arm 1, how that affect regret and how that affect the violation. Okay, so you will see in instance 1, then if we increase the C from 0 to 1, then the regret will decrease. Okay, then the violation will increase. Okay. The sweet spot is the optimal solution when you set the C equal to 0.4. Okay. So now if you look at instance 2, then the optimal solution is slightly perturbed from instance 1. So this will be the optimal solution for instance 2. Okay. And if you plot this picture, you will see again, as C varies, the regret will decrease, the violation will increase. Okay. But the sweet spot is different. Okay. So now if you look at these two instances together, okay, so because your algorithm will not have knowledge about the instance, right? The algorithm is an online algorithm, only depends on the samples you get. So if the samples is the same, even they come from two different instances, then the decision will be the same, and the number of pools will be the same. Okay. So I mean, it's more this, it's still heuristic. You can make it very rigorous, but I'm here just talk about from a high level, right? So now if you look at this and then you look at when I vary C from 0 to 1, then when C is less than this point, which is intersection between regret of instance 1 and the violation of instance 2, if C value is less than that, then your regret will be larger than square root of k. Okay, but when C is larger than that, the violation from instance 2 will be larger than square root of k. Okay, so that means whatever the policy you use, whatever the learning policy is used, either you will have a high regret in instance 1 or high violation in instance 2. That basically means achieve log regret is impossible. The best you can achieve is square root of k in the constraint case. Okay, so what's the reason for that? The reason for that is if we look at unconstrained case, we are looking at classify whether arm1 is better or arm2 is better. If their distance is a constant, then you have lots of rooms to making errors, right? But for the constraint case, you need to get the exact number, right? You need to get that exact randomization to be optimal. So the precision for your decision is much, much higher than an unconstrained case. So because of that, because of the randomization issues, the regret or the learning part also become much harder, okay? Compared with unconstrained. Okay, so that these are the fundamental differences. Okay, any question? Yeah.
So I can think of this constraint as being in the objective as with some kind of Lagrangian, right?
Mm-hmm.
Then the first term in the objective has the gap, but the second term does not have the gap. Is there an assumption you can impose so that the second term also has a gap? Essentially, I think you want to make both of them strongly convex somehow. The first one is, but the second one is not, right?
Well, I mean, the convexity is not the issue, right? You can always have a unique solution. The problem is the solution is a greedy solution or the solution is a randomized solution. Because sometimes the unique solution is bad because you don't have the flexibility in learning, right? In the discrete case, basically, let's say I have a learning, but I can tolerate a larger learning error, it still allows me to separate the two. But here you cannot, okay? But I think the question actually relate to one thing I want to mention later. What's the problem using the primal dual and to convert the problem in an unconstrained problem, right? It turns out, you can imagine if I use the primal dual solution, whenever the dual variable is fixed, is LP, I get a greedy solution, right? None of the greedy solution is optimal, which means use the primal dual, whatever the lambda you choose, you cannot recover the optimal solution. Why is that? Because the optimal lambda you give will give you a set of greedy decisions. The optimal solution is a randomization of these greedy decisions. And you don't cover the randomization. Yeah, so that's why I also make the problem is really interesting. Yeah. Yeah. Cool. Yeah. Okay. Any other questions? Okay. So now let's look at what are the solutions we can develop. Okay. So even there's a fundamental difference between unconstrained and constrained problem. One thing they are in common is even for constrained problem, if you use occupancy measure, you can still formulate the CMDP as a linear program. Okay. So if you use a model-based solution, then you can use the LP approach. So therefore, there's a lot of interest over the last few years of solving unknown CMDPs, basically for solving this constraint reinforcement learning problem, use this linear programming approach. Okay, so if the Markov chain is known, CMDP is not new problem. It has been a long history of looking at a solution. For example, Eitan Altman has a very nice book on that. But for unknown CMDPs, I think there's still a lot of open problems. Okay? So the earlier attempts to solve these unknown CMDPs is using model-based solution, where you learn the transition kernel, then you formulate it at LP, then you find the solution for LP, then you get more samples, you refine the model, then you get a better policy. Okay. Then there's also solutions which use a partial model-based solution, use the primal dual, but you use the transition kernel in one of the primary in the primal solution. Okay. Then there are solutions using simulators, right? Using simulators to generate data, then you can use actor critique algorithm with simulators. Okay. So what we were interested is by the time when we look at the problem, there are no model-free approaches for solving CMDPs. Why we are interested in model-free approaches? Because for a lot of the reinforcement learning problem, actually it's very hard to model the system. So there are two aspects of that. One is the model could be very, very complex, with a high dimensional state space. So that makes the learning the transition kernel to be very, very difficult. Okay, so that's one. And the second one is sometimes even the state space is unknown. For example, I say I have an autonomous car, self-driving car on a street. What is the state space? It's impossible to get all possible state space, right? For those kind of applications. So because of that, like in a lot of applications, not all of them, we prefer model-based solution. Even you look at these like applications of IL with a very high visibility, like AlphaZero, ILHF or GPT fine-tuning, they all use a model-free approach. So that's basically the motivation we want to look into whether we can use model-free approach to solve CMDPs. So that basically leads to the third question I want to discuss is how do we achieve, for example, sublinear regret and zero violation with a model-free approach. Okay. So for me, this work is particularly interesting because it's a combination of some old ideas from optimization and old ideas from queuing. You will see queue shows up, and also some new ideas about online learning. How do we modify the algorithm using online learning to control the regret and okay, so let me get into that. So this again is a CMDP problem we want to solve. We have constraints here, and we want to maximize the reward subject to the constraint. Okay. So what's the first idea? As Sevcik already mentioned, because the constraint problem, if you're facing a constraint optimization problem, then one of the first idea is to use a dual approach, right? Add a Lagrange multiplier, make it unconstrained. Okay, so we can do that. So we can add the Lagrange multiplier lambda, and then have the primal problem, which is the reward plus the lambda times the utility, because basically this is a penalty term. Then we can update this lambda according to some subgradient method, right? Okay, so this actually you can prove convergence, right? They will converge in a stochastic sense to the optimal policy. But there's no regret analysis by the time we look at this. Okay, so what we are interested is not only at the end we get a policy which is safe, we also want to see when we try to learn the policy, whether we can learn in a safe way. In this setting means the violation will be small, right? We want the average violation to be below zero. Okay, Any question?
What if there, so in practice, I'm gonna take something like this. I'm gonna replace the policy with a big model, maybe like a deep neural network. Sometimes the capacity of that model is not gonna be large enough that I can actually hit the constraint.
Right.
What happens then?
So I think in that case, I mean, that's just my my guess, right? We don't have any theory back there. But my guess is you will find a policy which will satisfy the constraint, if it's possible, under the policy class, then with the largest reward you can get. So basically, it becomes a constraint problem, not only constrained with the utility, also constrained on the set of function you can choose to form the policy.
And now what if among that set of functions, there exists no function that can satisfy the constraint that you have?
Then you will see the constraint blow up by running the algorithm. Yeah. So I think in the constraint setting, what we observe is constraint is actually the first order objective. The algorithm will always try to satisfy the constraint first, then after that, try to maximize it. Okay. Yeah. Even the rewarded objective, the constraint, they try to set. Because from primal dual approach, you can see if the constraint cannot be satisfied, then the lambda will shoot up. Then it will dominate the primal objective. Then you basically, the goal is to minimize the constraint violation. Yeah.
Sorry, this might be a naive question, but you mentioned in the motivation that one of the motivation for the difficulty here is that if you make action, you have to consider how you get into the current state. So the policy class research within, so it looks to me that it's still Markovian policy class, but the optimal policy should be Markovian or history.
We can still have a Markovian policy. So it's an excellent question. So even in CMDPs, you can still have a Markovian policy, but that policy depends on initial condition.
Yeah. So if I understand correctly, if you solve the optimal policy, you run for one stage. If you get to the new state, in principle, it sounds like you have to solve another constraint MDP starting from the second stage.
No. So you can solve a single policy, which is the Markovian, but it's initial state dependent.
Okay, I see.
Yeah. So you can solve the problem for the whole horizon, but if you change the initial distribution, then the policy will be different.
All right.
Yeah.
Thank you.
Yeah.
So I follow that question. You get a time consistent policy.
It's Markovian, so it's time consistent. It only depends on the initial condition. So time consistent means even the time changes if the state is, but here we're looking at episodic case, so I don't think it's related.
Right, so think about it. If you provide it like a family equation, then your policy won't be like this time consistent. The basis says, okay, well, you start like for a T period problem, you get the policy, and then now you move on to the next period. Then, okay, you resolve it. That policy probably will be different from.
Yeah, right. So if you resolve that from time step one, remember, unless you give what are the budget remaining, what costs occurred in the previous step, then you get consistent. Otherwise, if you have a different budget, then you get different policy, right?
But you update the budget.
Then it will be consistent as well. But the budget is random, so which means you have to design one policy for every possible budget. That's very expensive. So what here is you design a policy for given initial condition. So then you have a policy which don't worry about the budget, only care about the state. Yeah, but when you change the initial distribution, then the policy changes. Yeah.
I'm confused. So earlier you said that there is no optimal lambda.
Yeah.
Oh, yeah.
Next slide. Yes, exactly. Okay, so exactly. I said earlier, there's no fixed lambda will give you the optimal policy, but I'm still using primal dual. Okay, so I think I already answered the question. If the lambda is fixed, it will not give you the optimal policy. But also let me briefly mention, if lambda is fixed, this is just a unconstrained MDP problem, so we can use the existing solution to control the regret. Okay, but for this pseudo reward, it's not the true. Okay. So maybe let me first give you the answer for why fixed lambda does not give us the optimal solution, but we can still use primal dual. Is because when we run this primal dual, lambda will vary. Lambda is a stochastic process now. Now, if you average your policy over this lambda, then you get optimal policy. So the randomization is done by lambda. So lambda cannot converge in this case. It has to vary. Okay, yeah. Okay, so that basically is one difficulty, like how do we control the distribution of the lambda to recover the optimal policy, right? The second difficulty is now if we want to quantify the regret, we can quantify the regret in terms of lambda plus lambda g, sorry, R plus lambda g using existing result for unconstrained problem. But this is not the true regret, because regret we only care about the lambda. Sorry, we only care about the R. Then how do we quantify the true regret using the reward only without taking into account this utility is also not straightforward by using existing solution. So these are the additional difficulties of this. Okay, so let me tell you what is the algorithm and tell you what are the main ideas and the analysis. Okay, so we have this algorithm we call triple Q. Okay, because it has three different Q values. One is a traditional Q value for the reward function. Okay, so you look at if the policy is given, what are the average reward you get? Okay, then you also have this Q value for the utility. Basically, when the policy is given, what is the utility you get right under that policy? Then you have the third Q value, which I like the most, which is the virtual Q, which is the dual variable, basically keep track of the constraint violation. Okay, you will see why it's called a virtual Q, because it's like the Q in Q. Okay. Then we have this two-time scale algorithm. Basically, it's a two-time scale primal dual algorithm where we fix the dual variable lambda or the virtual Q every frame. Each frame has k to the power of alpha episodes. Then within each episode, when this virtual Q or the dual variable is fixed, we solve an unconstrained Q-learning problem. Okay. Then from frame to frame, we will update this virtual Q. Okay, so that's how the algorithm works. And then getting into more detail, at each step, as I said, we use a Q-learning algorithm, but the Q-learning algorithm is based on the pseudo Q value, which is a Q value for the reward plus this virtual Q times the Q value for the utility. Okay, so that's basically the primal objective. So we take a greedy action based on that. Then after each action is taken, we use a SASA type algorithm, is on policy Q-learning to update the Q value for the reward and the Q value for the utility. The difference is we're adding this UCB bonus term to encourage the exploration and also make sure the estimation we have for the Q and for the C are the overestimation of the Q and the C under the optimal policy. Okay. So that's what happens at each step. You can see the memory complexity, why it's model free, because we are not learning the transition kernel. We are just keep tracking of these Q value for state action pair. So the memory complexity is S times A times H. And also the computation is very simple because each time you only require a greedy selection and also update for the current state action pair. So both memory complexity and the computation complexity. Okay, so that's the advantage of model freedom. Then from frame to frame, we will update this virtual Q value. And also here the modification is other than just update according to the subgradient method, we're adding this called a pessimistic tightness constant into that update. I will explain why we need that. Okay, there's a minor detail. We also need to change the Q value slightly to add more optimism from frame to frame. Okay, so that basically is the output. So it's a combination of the unconstrained Q-learning, SASA plus UCB bonus, plus this virtual Q. Okay. And what is the guarantee you can get? The guarantee you can get is we can get a sublinear regret, where the dependence on the horizon or the number of episodes we have is k to the power 0.8. Then delta here is the status condition constant. Okay. Then we can achieve zero violation and the memory complexity is model free. Okay. So basically use this approach, at least we can achieve a sublinear regret and zero constraint violation. So analysis wise, how do we get there? As I said, to bound the regret, we are bounding the Q value, right, under the policy, but Q value for the reward only, we don't, yeah. Okay.
Can we go back to?
Yeah.
So you said square root is inevitable, but then what you have is 4/5.
Yeah, yeah.
So do you have a like formal square root lower
Yeah,
bound?
that's for part 4, my fourth question. Answer. Yeah, yeah. So, but it's good because the boundary now is tight, and there will be a very interesting observation I want to point out later, which help us to reduce that to square. But that will require some additional assumptions. So there are still lots of interesting questions need to be answered.
And what about the H dependence, the H power 4?
That can be reduced as well. And actually, the final result, I can tell you, S and A will disappear. It won't depend on state action space. Yeah. But it will depend on something else. Yeah. Okay, any other question? Yeah.
The present dependence on H for the following reason. If we go back to something like the bandit example that you have, if we have a very, very, very long episode, then the cost that we're going to have as a random variable summed of the whole episode is going to concentrate very fast over the mean of whatever stochastic policy we're using.
Right.
So I would imagine that long episodes actually makes it easier to estimate whatever we need to estimate in terms of constraint violation.
So here the difference is when I say episode here, episode is 1/4 in the bandit setting. So here I talk about horizon. So we look at like K episodes. So each episode you can regard as a pool. So what H shows up is like in bandit, right? The reward is bounded between 0 and 1. So H here become kind of upper bound on the reward you can receive each episode. So therefore, when H increases, the gradually. Okay. So let me quickly tell you the analysis. I just tell you what are the interesting ideas behind it, right? So we start with the Q value for the reward. We know that cannot be bounded because our decision is not based on the Q value for reward. It's based on the Q value for the pseudo reward. So therefore, we need to add this virtual Q plus the Q value for the utility into the equation. Then we based on the UCB bonus, we can say this one is more likely to be 0 with high probability, okay? But by adding these extra terms, not only these terms need to be added, and we're adding different terms. You can see, so this is our utility under the optimal policy. This is the estimation we get. It's not the true Q function for the utility, right? So therefore, by adding that, we have some lots of extra terms, which I called phi here, okay? Which actually is a very long term. But the very interesting thing here is this term actually can be related to be the drift term if you use the Lyapunov function of the Q square. So if you use this Z square as a Lyapunov function, like virtual Q, and if you look at the drift term, this drift term actually match this phi, okay? So which means by connecting the true regret with this virtual regret, you can connect that, use the virtual Q or the drift of this virtual Q as a bridge, okay? So that's basically the idea. We can analyze this virtual Q, use the drift method, Lyapunov analysis for Qing, and we can bound that, okay? So now our next question is how do we bound the violation, okay? It turns out the violation can be coupled with virtual Q as well, because if you look at this virtual Q evolves as arrival rate lambda rho, which is a threshold for the constraint, then minus the cost you accumulate, right? If we do the standard linear recursion, you'll find the Q length at time K or episode K is upper bound on the total arrival minus the total service. And what is this term? This is the violation. So the virtual Q length at each step or each episode is upper bound on your violation, okay? So now if you look at that, we know since we are making greedy decisions, right? And we know how large the Q value need to be. The Q value need to be at a value such that these two are comparable, because otherwise you are only consider reward or only consider violation, right? Only when these two are comparable, you are making decision based on both violation and the reward. So therefore, if our choice of the eta is k to the power 0.2, then the virtual Q value need to be at that order as well, which means the violation will be need to be that order, okay? So the question is, can we make it smaller, right? So here comes the idea used in queuing by adding this tightness, right? Because by adding this tidiness constant, what happens if, again, you do the linear recursion, then the upper bound on this violation is not the virtual cube, but the virtual cube minus something related to this constant and the number, the length of the frame as well. Okay, so that means you can still drive up the virtual cube length to be k to the power 0.2, but the violation can drive down by controlling this tidiness constant. Okay, this is actually an old idea used by Srikant for internet congestion control. When they design adaptive virtual queue, they set the virtual queue system with a slightly reduced capacity. So the virtual queue length can send early signal about congestion to the congestion controller. That basically happens here as well. So we are sending the early signal by using, by adding this constant. And with that, you can bound the, let me get into the result again, make the constraint close to 0 on average sense, and bound the regret and get same. Okay, so let me, given the interest time, let me jump into right out into the drawbacks of this algorithm. So one thing CJ has asked, this regret upper bound does not match the lower bound. We know this lower bound actually is achievable if we use a model-based approach. If we learn the transition kernel, then we can do, right? But the model-free one, we cannot do. Second one, you may also already have the question. If we run this algorithm, you can see lambda changes slowly. When lambda change, you get a different policy. None of these policies is optimal. Only you average over this policy, you get optimal policy. The policy does not converge. Actually, each frame, you either have a huge violation or huge regret, just they average out, right? You don't get the optimal policy at the end. You just like run these policies and slowly, hopefully on average, they have good performance. So that's a huge problem too, okay? So that basically leads to the fourth question. The last question I want to answer is, can we do better, okay? It's not easy. I mean, we cannot do that in the general setting, but we can do that in a setting which is fairly general, but with additional assumptions, okay? So first of all, what are the difficulty, right? So difficulty, as I mentioned, is a constraint problem. The constraints lead to randomization, okay? The randomization make the problem hard because the learning have to have a high precision. So that's a problem. So the randomization, as I mentioned, is a problem, okay? For making the problem really, really hard. So now let me, before I tell you the observation or the result in the literature, it's a very important structural property. Let me first give you some notation definition or like terminology. Let's say we now classify the action or the decision the agent makes into two categories. One is the greedy decision, another is stochastic decision, right? So it's a very intuitive characterization. Let's say this is my action space. This is the policy I'm going to use. So for example, in state 1 and step 1, I choose action 2 with probability 1. So this will call the greedy decision. And if I randomize in that state at that step, I will call that a stochastic decision. Okay, so if a randomization is involved, it's called stochastic decision. And if greedy decision involved, it's called, if it's not randomized, it's called a greedy decision. Okay, so why I need to separate these two? Because I want to bring up a result which is in the literature for a long time, but it hasn't been well utilized. It's called limited stochastic. Okay, it's called limited randomness by changing the name. Okay, it says if I have for CMDP, there exists an optimal policy where the decision you need to randomize is at most the number of constraints you have. So for example, if you only have one constraint, you only need to randomize at one state. You don't need to randomize at other state. For all the other state, you can take greedy decision, just to need to randomize at that one particular place. But remember, this is one optimal policy. You can have many other policies randomize more, but there exists one optimal policy with this limited randomization. Okay. So now, why this helps? Because now we can, yeah.
Do you know which state that you are doing the randomization?
We don't. Yeah. So that's exactly also the challenge we have to overcome, right? So how do we actually, first of all, learn where to take greedy decision, where to take randomized decision, then we further learn how to randomize, okay? So, but it helps because if the number of constraints is not so large, then learning where to randomize turns out to be relatively easy than learn how to randomize. So the precision of learning where to randomize is not as high as the precision required to learn the exact randomization, okay? So actually the idea we come up with is we can think about first the problem as a classification. So at each state, then we can ask the question, at this state, is this the action necessary? Can we remove this action, still have optimal policy? If this action is necessary, is this action greedy, which means greedy is sufficient for us to retain optimal policy, or we have to randomize and involve this action A. Okay, so we can first think about we solve this classification problem and to identify where to randomize. Okay, so now how do we do that? How do we do that? We can use the algorithm I just talked about, the triple Q algorithm, or in fact, any algorithm with sublinear regret and sublinear violation. We can do a testing, right? How do we do testing? We have CMDP1 with original action space and CMDP2 with reduced action space. So let's say I'm testing A2 to see whether A2 is necessary, okay? So if A2 is necessary and we remove that, then what happens? So either the constraint will be violated or the regret will be, or the reward will be smaller, right? So these two will not have similar performance if I remove some action which is necessary. So therefore, I can run triple Q algorithm for both settings and compare the performance. And if the performance is similar, then which means I can remove that action. Sorry, I mean it's not necessary. I think I typoed here. And otherwise, I need to keep. Okay, so I can do the same testing for greedy decision as well. Say, if I take greedy decision in that state, will that be sufficient, right? If the performance is similar, I will say it's greedy. Otherwise, it has to be stochastic at that condition. Okay. So it turns out this problem with the result we have in the triple Q, from learning perspective is easier. We can show if the CMDP are well separated. So there are two assumptions we use. One is CMDP we consider need to be well separated. Well separated means if you take different actions, the reward and cost has separation. They're not close. One of them has. Okay. And where we show like after pruning phase with only k to the power 0.25 episodes, with high probability, we can identify the minimal action space, where the minimal action space will include at most these HS plus N actions. Okay. And which will involve, if you construct a stochastic policy from here, then you can only randomize at N actions. It actually tells you where to randomize as well. Okay. So for example, here you can either, for example, what the minimal action space look. Okay. So now after we,
the O tilde k power 0.25, there should be some HSA dependence there, right?
But the order is smaller. Because then later in the second and third phase, we have squared k without S and A, but it has H. So therefore, this one is negligible if we look at large case now.
Yeah. But what I meant to ask is that even polynomial dependence, or can it be
polynomial dependence?
It is polynomial.
So in fact, the real number, the exact number is H times S times A times log K.
Oh, okay, thanks.
Only thing which is not polynomially dependent is N, you will see. So that's the trade-off. Okay. So I'll ignore the proof. Then the second step is, let's say we find this minimum action space. Then from this minimum action space, we can have 2 to the N greedy policies. Okay. So again, we don't want to use a model-based solution. We don't want to form LP to recover the transition kernel, but we will form a LP for this greedy policy. So for each policy, we can evaluate the Q function or value function for the reward and the value function for the utility. Then you can formulate LP where it's policy based. Okay, so you solve this current objective given you can only combine these M, which is the 2 to the N greedy policies. Okay. Then you can use the idea of evaluating, then solve that, use a solution to further evaluate, further solve, and you can control the regret of that. And you do this square root of k round, and each round includes square root of k episodes. Okay. And as I said, because the dependence on n is exponential, so if the number of constraints is very large, the computation complexity will blow up. Okay, the number of policies need to be very. Okay. Then after that, then you learn basically 2 to the n greedy policy, which is still large, even n is a small number, right? But at the end, you want to get a single stochastic policy. Then what you can do is you can just run this mixture of these m greedy policies. Then you record the occupancy measure. Then you can recover the single one greedy policy, one stochastic policy from that. And that stochastic policy will randomize only at capital N locations. Okay, so most of that will be greedy. So this is the final result. It achieves a regret, which is independent of S and A, but exponentially depends on capital N. Okay, so that's the price you pay. And the complexity is again this one, and only work for small n for now. And you also get one policy, not varying over many different policies. With high probability guarantee, it will satisfy all the constraints and close to the optimal value. And also we have a matching lower bound, says the lower bound, even the MDPs are well separated. The best you can do is h times square root of k. So basically the difference is a polylog. Okay, I think that's, again, just want to mention the problem hasn't been fully solved because first of all, it's required n to be small. We don't know for large n what happens. On the other hand, there's some negative result, which is not directly related to this model, related to the discounted CMDP when discount factors can vary according to the constraint. So you have a different constraint, have different discount factor, where the negative result says that problem is NPR. If the number of constraint is is equal to twice of the state space. So that also shows intuitively, if the number of constraints is large, the problem actually is a very hard. Okay, but it's a different setting, so I don't have a formative answer. What's the difficulty level for episodic? So we actually have looked at as a variety of problems related to this constraint setting, not for just for MDPs, but also for banded online control and convex optimization as well. And these are all my collaborators. That's all I want to say. And thanks, everyone. Yep.
The that you showed about having n places where you have to do stochastic policy, does that relate to some kind of Carey-Theodori theorem?
Related to what?
Some kind of Carey-Theodori theorem?
It's a very simple result, actually. If you look at the LP formulation for CMDP, and you ask a question at the extreme point, how many zeros the Q needs to have, how many equations you need to have. And if you just do that count, you will find like the number of zeros is very large, which means lots of places are greedy division.
Okay.
So just look at the LP 101, you'll get it.
Got it. Okay, okay, nice.
But it's underutilized.
Right.
Yeah.
Another question? If not, let's thank Lei Ying.